Hello everyone, this is question 2 of the NZQA 2022 Scholarship Chemistry exam. Let's move on. Let's move straight into question or part A. The molecules in fats, solids at room temperature, often of animal origin, and oils, liquids at room temperature, often of plant origin, are triglycerides. A single triglyceride molecule is a triester of glycerol, propan 1,2,3-triol, and 3 fatty acids, long chain carboxylic acids. The molecules can be saturated or unsaturated, and the 3 fatty acids in a single triglyceride molecule can be the same or different. Triglycerides X, Y, and Z are 3 different molecules found in common food products. Within each molecule, the 3 fatty acids are identical. Use the 2 fatty acids given below to draw a possible structure for triglycerides X, Y, and Z, considering the descriptions given. With reference to these structures, justify the observed variation in the states of the 3 different food products. You do not need to use expanded structural formulae, and any stereochemistry in the structures may be labeled rather than drawn. So they tell us triglyceride X is saturated in a major component of butter, which is a solid at room temperature. Triglyceride Y is unsaturated in a major component of olive oil, which is a liquid at room temperature. And triglyceride Z is unsaturated and a major component of margarine, which is also a solid at room temperature. So triglyceride X is quite easy to figure out because they tell you it's saturated, and of these two, only the left one is saturated. So then you'd have triglyceride, and glycerol is CH2, CH2, and then with OHs, because I tell you it's propan 1,2,3-triol. And then the triglyceride would simply be an ester of these alcohol groups. So let's say we added C-double-bond-O, and then let's say CH3, in which case this is ethanoic acid forming a triester with glyceride or glycerol. Okay, so that means X must be the initial triglyceride, so CH2, CH2, and then you have the O, and then you would have C and then double-bond-O for the acid. And then they say it's CH2 16 times and then CH3, so you can just write that out. So CH2 16 times CH3, and you do that 3 times. CH3. Okay, and the justification for this is, well, you can just say it's saturated, but because it's a scholarship, you have to attack every detail, and the other detail that you have is a solid. So firstly, saturated, therefore no double bonds. And the one on the right here has double bonds, and so it's unsaturated. So it has to be the one on the left. And you also know it's a solid. And that can be justified by the fact that this sort of chain here is very long and it's very linear. So you have, because long linear chains, and because of that you have that they can stack or pack closely, and so then you have strong intermolecular forces, low melting point, high melting point, high melting point, therefore solid at room temp. Okay, we've justified both parts of the description. Now we move on to triglyceride Y. This has unsaturated and it's a liquid. So obviously the unsaturated one has to be this. And if you look at triglyceride Z, it's also unsaturated, but instead of being a liquid, it's a solid. So the only differentiating factor between triglyceride Y and Z is the fact that one's a solid and one's a liquid. And we know we have to use this fatty acid with the double bonds in it because they say that all the fatty acids used in the triglycerides are identical. So what's the difference between one form of this fatty acid and another form of the other fatty acid, or the same fatty acid? Because it has a double bond, we know it exhibits cis-trans isomerism, which means that one of y and z is cis, and one of y and z is trans, and we have to deduce which one is cis and which one is trans based on whether or not it's a liquid or a solid. So let's think about this. Firstly, we can start with the CH2s. So CH2, CH, CH2, and then the O's, and then the C double one O's. Oops. And then we would have, it starts off with CH2 7 times. So CH2 7 times. And then we have a double one. So CH2 7 times, CH2 7 times, C double one, C double one. And the same thing happens here. So CH2, CH, CH2, and then O, 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 C double one O, C double one O, C double one O, CH2 7 times, CH2 7 times, CH2 7 times, carbon, double one, carbon, double one, carbon, double one. And we're trying to figure out which one's cis and which one's trans. And the justification for this is quite simple. We know Y is unsaturated. So that's the first justification point. And the second, therefore there are double ones. The second justification point is quite simple. We know Y is a liquid. And if it's a liquid, that means intermolecular forces between the molecules are quite weak. And this is sort of knowledge that you need to know. Cis molecules tend to have weaker intermolecular forces because when you have cis molecules, let's say it's like this, and you would have CH3, I don't know, and you had HH, you have this sort of kink shape, and because of the shape, the original linear sort of structure that I would otherwise have without this cis structure is disrupted. And because you don't have any linear structure, it's the same logic as here. You don't have linear structure. They stack or pack less closely. They don't stack together as well. So you have weaker intermolecular forces. You have a lower melting point, and so it is a liquid at room temperature. And so, you would have, because cis, not so linear, it's kinked. And so no good packing. When you're writing out the exam, please don't copy my grammar. Let's see, weak intermolecular forces, low melting point, and so it's a liquid at room temperature. So we can draw this out. So the H's would be on the same side because it's cis, and then we have the rest of the molecule here. So CH2, and then 7 times, and then CH3. So we can do that 2 more times. CH2 7 times, CH2 7 times, CH3, CH3. And then the opposite would then be true for the triglyceride Z. So you would have a trans isomer. And the reason for this is because if it's trans, this follows more of a linear shape. It's still sort of kinked, but the sort of linear trend is still there. That doesn't look too linear, but it's more linear than you would get in a cis. And so I won't write this out. Unsaturated. I won't write this out fully. R C double bond C bonds. Solid, because trans, more linear, and same logic applies. So we can draw that out too. Again, we have CH2 7 times. It's the same fatty acid, except instead of cis, we have trans. And we're done. So we've justified which of X, Y, Z are considering the descriptions. So part 2 of question 2a here. It is difficult to clean fats and oils from dining plates, cutlery, or our skin using hot water alone. Detergents and soaps contain substances known as anionic surfactants, which are often used to assist with the cleaning process. The anionic surfactants found in soaps are produced from the hydrolysis of naturally occurring fats and oils. A common water-soluble surfactant in soap is sodium dodecanoate, which is produced from the hydrolysis of triglycerides found in coconut oil. Explain why water alone is not able to clean away fats and oils, and propose reasons for the use of surfactants such as sodium dodecanoate in the cleaning process. Okay, again we have 2 components to this question. Firstly, why water alone is not able to clean away fats and oils, and secondly, why surfactants such as sodium dodecanoate are used in the cleaning process. Okay, so firstly, why is water alone unable to clean away fats and oils? Fats and oils are typically triglycerides. So, let's see. Fats and oils are typically triglyceride molecules, or they have triglyceride molecules. O, and then CO, and then yada yada yada, depending on whatever fatty acid is attached. And they consider why water alone is not able to clean away these molecules. So water, as we know, is a polar molecule. And we know that the hydrogens are positively, or have a delta positive charge, and the oxygen has a delta negative charge. And the thing is, water, because it's a polar molecule, because these triglyceride molecules, they're long, and as we can see here, they basically consist of long non-polar chains. You have a whole bunch of CH3, CH2, 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 and so on, which are all non-polar, and it's all very long. So that means the triglyceride molecules are predominantly non-polar. Predominantly. Obviously, there are still some polar aspects to it, but in the grand scheme of things, it's still too big to be considered polar, and so it is considered non-polar. Water, on the other hand, is polar. And so this is a very typical scholarship exam question where they ask you to consider polarity and whether or not that contributes to solubility, or in this case, it's whether or not it can mix. So water molecules are very, very polar, and so what happens is H delta plus. Any neighboring water molecules would form hydrogen bonds like that, and because of their high polarity, these water molecules are held together very strongly. And these non-polar water molecules would bond with each other, and then the water molecules would be unable to be separated by the oil molecules, and the oil molecules would be unable to be separated by the water molecules, because the attractions between these two are way too weak, because one is polar and one is not. And so you can't overcome any of the networks of intermolecular bonding in either of these substances, and so you can't mix fat and oils. So therefore, fats and oils do not mix with water. And then that's why water alone is not able to clean away fats and oils. That's the first part of the question. Second part of the question is why use of surfactants is used. Surfactant in this case is the sodium dodecanoate, so it would be CH3, CH2, and then 10 times, and then C, and then that is a carboxylate ion with an Na plus. And so what's useful about this is specifically its ionic charge. So usually we can ignore the sodium, but it's this ionic charge here that we're concerned with. And also this part is highly nonpolar, because again, it's another very long chain of alkyl, or CH3, CH2, CH2, and so on. It's a very long chain of nonpolar groups to it, and so it itself is very nonpolar. And so this is able to mix with oils and fats. because of its ability to attract other non-polar substances, such as the fats and oils that were also non-polar. But you also have this ionic charge here. This is ionic. And what you know about ionic substances is that they tend to dissolve in water quite well. Think about salt. Salt is an ionic substance, Na plus and Cl minus. It dissolves in water quite well. Obviously, there are exceptions to this rule, like barium sulfate. But in the general case, ions dissolve quite well in water, simply because these ions are very, very charged. They literally have an extra negative charge to them. And compared with this, in relation with the positively charged hydrogen in the water molecule, the forces of attraction are strong enough to separate not only the water molecules from each other, but also these sodium dodecanoate molecules from each other as well. So what you have is, on one hand, the nonpolar chunk of the sodium dodecanoate molecule is able to mix with oils and fats. And on the other hand, this ionic part of this sodium dodecanoate ion is able to mix with water, because the ionic forces are strong enough to overcome the polarity of the water molecules. And so what's basically happening is that the sodium dodecanoate acts like a bridge between the fats and oils and the water and allows them to mix. And so before, we only had fats and oils and water, and they did not mix quite well. And the sodium dodecanoate basically acts as a vehicle. Vehicle's not a good word, but it's like a medium. Not medium's not a good word either, but it's like the methodology, or the molecule which sort of facilitates the mixture of water and fats and oils. And so that allows, if we link it back to the question, that allows fats and oils to be used to clean, that allows water to be used in combination with the sodium dodecanoate to clean the fats and oils off the dining plates, cutlery, or whatever. So now we come to part B of question 2 of the 2022 NZQA Scholarship Chemistry paper. During a classroom demonstration, a teacher prepared a small beaker of dilute copper 2 sulfate solution, CuSO4, which was pale blue in color. Addition of a small volume of ammonia solution, NH3, to the beaker caused a pale blue precipitate to form. And then addition of further ammonia solution caused the precipitate to disappear and the solution to darken into a deep royal blue color. Addition of dilute hydrochloric acid solution to the beaker caused the solution to lighten in color and a pale blue precipitate to form. Addition of further dilute hydrochloric acid solution led to the precipitate disappearing, leaving a pale blue solution. Justify the observations made during each stage of this classroom demonstration. You should identify the species responsible for the observations and use equilibrium principles and balanced chemical equations to support your justification. So this is a sort of classic justify why things happen or why observations are observed based on equilibrium principles. And the thing is with this question is it's quite hard to do if you don't have the prior knowledge required, because there are certain equilibria that are established in this solution that you simply just don't know about, in which case you'd be screwed. But hopefully you do know about these, and if you don't, I will be teaching them right now. So firstly, pale blue in color for the initial copper sulfate solution. So copper sulfate is just a mixture of copper ions, or copper 2 plus ions, and SO4 2 minus ions. Sulfate ions are colorless, but this is light blue, so pale blue. So that's why it's pale blue to begin with. But then you added a small volume, or the teacher added a small volume of ammonia solution. And so what happens is the ammonia reacts with water and causes hydroxide ions to be formed. Ammonia in this case acts as a base and accepts a proton from water to form a hydroxide ion, and it basically makes the solution more basic. And what does that do? Cu2 plus then enters into equilibrium, or 2 of hydroxides, with hydroxide to form copper hydroxide. And this is something that if you don't know, then you don't know, but if you do know, then good. Copper hydroxide is a precipitate. And in fact, copper hydroxide is a blue precipitate. So what's happened here is NH3 is added, solution becomes basic, hydroxide ions are formed, and the hydroxide ions enter into equilibrium with copper 2 plus, and it forces the equilibrium this way, as a result of Le Chatelier's principle, to form copper hydroxide, which is a pale blue precipitate. So that justifies the first part of the ammonia solution. But then they say addition of further ammonia solution caused the precipitate to disappear and the solution to darken into a deep royal blue color. And so what happens is, this is another equilibrium that is something you should just happen to know. The copper enters into equilibrium with ammonia to form this complex ion. Oh, sorry, not 3, not 4. 3 and then 4 and then 2 plus. And there's 4 of these. So copper enters into equilibrium with ammonia solution to form the complex ion given by this formula. And basically, as you add excess ammonia to the solution, what you have is any copper that was in the solution would be forced this way. And it would form this complex ion, and this complex ion also happens to be royal blue. So that justifies why the solution turns into a deep royal blue color. And as you remove copper 2 plus from the solution, it actually forces this equilibrium to go the other way. Because as you remove copper 2 plus solution, more copper hydroxide will be able to dissolve, and it increases the copper 2 plus again. And so that justifies why the precipitate disappears. So what's happening is the addition of NH3 or excess NH3 has done 2 things. The first thing is it's formed a complex ion, which is a royal blue color, which is why the solution turns into that royal blue color. And the second thing is because it's the NH3 has removed Cu2 plus from the solution, the first, or this equilibrium here, has to be forced backwards. And so more copper hydroxide dissolves and the precipitate disappears. And then the second part is addition of dilute hydrochloric acid solution to the beaker causes the solution to lighten in color and a pale blue precipitate to form. So what happens if you add HCl? HCl obviously is acidic, and it would fully dissociate in water to form hydronium ions and Cl minus chloride ions. And so the solution has become acidic. And because the solution has become acidic, any NH3 which is in the solution would react with the hydronium ions in equilibrium to form NH4 plus water. So what's happened is basically the NH3 has neutralized the HCl, and it's been converted into ammonium, NH4 And because we have decreased the concentration of NH3 based on this equilibrium, this equilibrium here would be forced to go this way, because the CuNH3, the equilibrium wants to restore the NH3 that was lost, and so we would lose the royal blue color, and so that's why the solution lightens the color. And basically the whole process is reversed. The NH3 is gained by this equilibrium, and at the same time copper 2 plus is also gained because this equilibrium here has shifted backwards. And because that copper 2 plus ion concentration has increased, this first equilibrium over here is shifted forwards. And so the amount of copper hydroxide increases. So the addition of hydrochloric acid has simply reversed the effects of the NH3. What caused the NH3 caused the solution to first form a precipitate and then give a royal blue color after excess ammonia was added. Adding the HCl cancels it out because it neutralizes any NH3, forces the royal blue color to disappear, and then it forces also Cu2 plus to enter into the solution again, which forces the Cu2 plus to precipitate with any hydroxide ions in the solution to form copper hydroxide. And then what they say is addition of further dilute hydrochloric acid led to the precipitate disappearing, leaving just the pale blue solution. So basically we've gone full circle. Adding the further dilute hydrochloric acid solution has left you with just the pale blue solution that we started with, which was the copper sulfate. So why is that? Because we've added excess or even more hydrochloric acid solution, any hydroxide ions in the solution would react with the hydronium formed by the HCl, and it would just give water. So any hydroxide ions in the solution has been completely neutralized by the hydronium, and this would probably be the situation where the pH is either equal to 7 or it's less than 7. The solution is either acidic or neutral. And so what happens is, because the hydroxide in the solution has decreased, this equilibrium is shifted backwards to replenish that. And so again, you have a dissolution of the precipitate, and the precipitate disappears. So what's happened in this question is, in this case, pH was still greater than 7, and so the hydroxide ions were still able to form an equilibrium here with the copper 2+ ions to form the precipitate. But as soon as you've lost so much hydroxide ions from the addition of further HCl, the pH drops below 7. The concentration of hydroxide is not significant enough for this equilibrium up here, to form copper hydroxide, and so you've lost all that copper hydroxide. And so this question is basically just considering a whole lot of equilibria, which hopefully you know by prior knowledge, and seeing what happens if you add something and how that affects concentrations of certain species, and how those changes to the concentrations of certain species affects equilibrium, which would cause concentrations of other species to change.